Welcome to this explainer. You asked us to explain me the cement chapter, so that's exactly what we're going to do. We're turning that dense engineering textbook chapter into a clean, visual study guide to help you crush your final exams. We are skipping the fluff and zeroing right in on the core chemistry and manufacturing parameters that you're actually going to be tested on.
All right, let's kick things off with a massive number. Look at this on the screen, 12 billion. That's 12 billion tons of concrete placed globally every single year. It's actually the second most consumed resource on Earth, right after water. It's literally the foundation of modern civilization. But that kind of scale, it brings some massive responsibility.
And here's the catch. For every single ton of cement produced, we emit 1 ton of CO2. It's a 1-to-1 ratio, and honestly, it's staggering. So as future engineers, nailing down this fundamental chemistry isn't just about acing a test. It's about learning how to tweak these materials to build durable structures that actually shrink our carbon footprint.
To get you ready for those exams, we've chopped the life cycle of cement into 6 easy stages. Cement as the essential binder, chemical recipes and oxides, the manufacturing process, hydration, testing quality, and finally, cement varieties.
All right, part 1, the essential binder, defining cement. So what actually is this stuff? Now, natural cement is a thing. People used to just crush up natural stones, but today we're focusing on artificial or Portland cement. Fun fact, it's called Portland cement simply because it looks a lot like Portland stone found in England. The key takeaway for your exam, though, is the recipe. It is a highly engineered mix of calcareous materials. Think calcium and magnesium stuff, like limestone, and argillaceous materials. Those are your silica, alumina, and iron oxides, mostly found in clay or shale. Moving right along to section 2, chemical recipes. Let's look at the oxides and compounds. You're definitely going to want to memorize this table. It breaks down the 4 main mineral ingredients of Portland cement. Tricalcium silicate, or C3S, is the big one, making up roughly 45 to 55% of the mix. Right behind it is dicalcium silicate, C2S. Together, these two silicates do the heavy lifting for structural strength. Then we have tricalcium aluminate, C3A, and tetracalcium aluminoferrate, C4AF, which play smaller but absolutely vital roles in how it all reacts.
But here's the thing. This recipe is a delicate balancing act. Your textbook spells out exactly what goes wrong when the balance is off. For example, too much lime? That's a huge structural liability. It makes the cement unsound, meaning it'll expand and crumble over time. Too much silica slows down your setting time to a crawl. Excess alumina causes unwanted expansion. And if you let magnesia creep over 2%, it straight up weakens the concrete. It is all about precision.
Okay, section 3, the manufacturing process, wet versus dry methods. So we have our ingredients. Now, how do we cook them? This graphic is a great side-by-side of the 2 main manufacturing routes. Up top is the wet process, where raw materials are mixed with water to make a slurry. It mixes incredibly well, but it takes a ton of energy to boil off all that water later. Down below is the dry process. As you probably guessed from your reading, this one is significantly cheaper because you skip the slurry step entirely, saving a huge amount of fuel when it's time to burn the mix. Listen up, because drawing the flow diagram for the wet process is a classic exam question. You really need to be able to map this whole journey out. It starts with taking your calcareous and argillaceous materials, grinding them down, and mixing them into that wet slurry. Then you feed that slurry into a rotary kiln fueled by coal dust, which produces clinker. Finally, you cool that clinker and grind it up one last time with some gypsum to get your final cement powder. Let's zoom in on that rotary kiln for a second, because it's basically a gigantic rotating oven with 3 distinct temperature zones. First up, the slurry hits the drying zone, around 400 to 600 degrees Fahrenheit, to bake out that initial water. Then it moves to the calcination zone, jumping to 1600 degrees. Finally, it hits the clinker zone at a mind-blowing 3000 degrees Fahrenheit. Just to put that in perspective, that's about a quarter of the temperature of the sun's surface. This is where the intense chemical reactions happen, fusing everything into those vitrified, glassy little nodules we call clinker. Which brings us to section 4, hydration magic, where cement finally meets water. Once we cool and grind that clinker, it's ready for hydration, the chemical reaction between the cement powder and water. Now, this reaction is highly exothermic, meaning it throws off a ton of heat. See those 3 distinct peaks on the graph? The first one happens the second water touches the particles. Then there's a dormant period, which is super important because it keeps the paste workable. After that, you get the secondary and tertiary peaks as the main strength-building compounds kick in over the next day or so. So hydration isn't just a one-and-done event. It's a dynamic, ongoing process. Now, you might be thinking, how on earth do engineers control all this? Well, remember our friend C3A from the ingredient table? It reacts violently with water. If you don't keep it in check, you get what's called a flash set. The paste stiffens up immediately, and you literally can't work with it at all. To stop this, engineers toss in a little bit of gypsum during that final grinding stage. The gypsum forms a protective layer around the C3A particles, basically acting as chemical brakes to delay the initial setting time. That way, you actually have time to pour and place your concrete. Once it's poured, our two silicates tag in. It helps to think of C3S and C2S as a relay team. C3S, the tricalcium silicate, is the sprinter. It hydrates fast and provides the main structural strength for the first few days. Then it passes the baton to C2S, the dicalcium silicate. C2S hydrates super slowly. It's playing the long game, driving the progressive long-term strength gain over the course of months or even years.
Section 5. Testing quality. How do we verify this strength?
To prove these chemical reactions actually did their job, we test. And before you even send samples off to a fancy lab, you can do some basic field tests with just your hands, your eyes, and a bucket of water. Visually, you're looking for a greenish-gray powder with 0 lumps. Thrust your hand into the bag. It should feel cool, smooth, and not gritty at all. You can also make a thick paste and drop it under water for 24 hours. A good batch won't crack, and it'll hold on to perfectly sharp, crisp edges. For the exact numbers, though, we head to the lab and cast these specific shapes. On the left, Figure A is a briquette specimen used for checking tensile strength, which, by the way, is usually pretty low in concrete. But Figure B, the mortar cube, is the main event. We test these cubes for compressive strength at standard marks, usually 3, 7, 14, and 28 days. Here's a quick exam tip for you. Cube specimens generally yield higher compressive strength numbers than cylindrical ones, just because of how the mechanics of the test work. All right, final part, Section 6, Cement Varieties and Specialized Uses. This is where we see how tiny tweaks to our oxide recipe create highly specialized cements. This table is an awesome cheat sheet for matching up British standard descriptions with American ASTM types. It really shows off the versatility of the material. Say you're building a massive concrete dam. The heat of hydration from a standard mix could literally crack the whole thing from the inside out, so you'd specify Type 4 low-heat Portland cement. Or if you're building in soil that's packed with harsh chemicals, you'd switch to Type 5 sulfate-resisting cement, which strictly caps that reactive C3A content below 5%. We can push this even further with blended cements. This is where we swap out a percentage of the cement clinker for industrial byproducts, like fly ash from power plants or slag from steelmaking. Doing this achieves two amazing things. First, it creates a much denser microstructure that boosts long-term durability, especially around saltwater. And second, it directly cuts down the amount of raw clinker we have to manufacture. Which circles us right back to where we started. Using blended cements is a huge step toward fixing the massive CO2 emissions of the industry. As you prep for your finals, getting a grip on this chemistry is step 1. So I'll leave you with this. With 12 billion tons of concrete being placed every single year, how will your generation of engineers innovate these chemical formulas to build a greener, rock-solid future? Best of luck on the exam.